Alrighty, well, hello and welcome to yet another day. So our announcements today are, firstly, I would just like to remind you that if you're ever not sure what you should be doing in a week, a good place to look is on Sakai. If you go to our homepage, at the bottom here are the weekly plans. There'll be one for each week. If you open that up, it'll tell you roughly what you should be doing that week. So for instance, today is Wednesday. We're covering section 3.7 in the textbook. I have some videos here you can watch. And then a couple of people mentioned they wanted the summary sheets, and yeah, I still am posting summary sheets. There will always be, links will be here to them. And yeah, as you can see, there's no quiz today. There's no homework due today. The next homework will be due on Sunday. And this page will also be where I post like class recordings, or you can look on the YouTube page. So yeah, so just keep in mind that that's a good place to look for things. Second on the list is, because we lost a week, our next exam is actually coming up pretty soon. It's only 2 weeks from today on April 15th. It will be essentially the same format as what we did on Monday, with the only exception being that, because I kind of decided that submitting things, having you guys submit things in OneNote was a little bit too finicky, and it wasn't clear when things were submitted always. We're going to change to submitting things in Sakai, just to make our lives a little easier. But I will still be returning your work in OneNote. So that's still where your work will show up when you want to see it graded. Which reminds me, quiz 7 is now graded. So the last quiz you took is now graded. And you can go into OneNote and see those. But just a reminder that everybody that completed it got a 10 out of 10. In the future, that might not be the case, but for this one, it was. So yeah, our next homework was due Sunday. The other thing I wanted to ask you guys is, so the Math and Stats Center typically used to hold weekly study sessions for Calc 1, but they can't really do that anymore online. So we do have some TAs that could be useful in this class, and so I'm considering setting up some study sessions. So they would be like 1 hour twice a week, where a TA would be available on a Zoom call like this, where you could just drop in and ask questions or talk with other students. So I just kind of want to get an idea of how many people would be interested in that. If you would be interested in attending those, like at least once a week, could you just type yes in chat? No, nobody would be interested in that. So it would be basically you can come and ask homework questions. You can ask, if it's an exam week, you can ask questions about practice exams. But that's not something you guys would find useful. Wait 1 second, my chat is not showing up here. Okay, there it is. Oh yes, you guys are saying yes, sorry. Cool, okay. So yeah, I might try to send that up, so look for details on that soon. The other thing was the announcement I sent out. Maybe let's just look at that briefly. So that would be here. So yeah, part of it was about changing to OneNote. So at the bottom here, there's a survey if you want to give feedback about how the class is going. I'd appreciate it. And the other thing is I am instituting a new policy where because sort of what I feel like is important in these types of classes is that sort of you just end up learning the material by the end of the class, and it doesn't really matter exactly when you master it as long as you get to mastery. And so if you score well on the final exam, what I will do is I will replace your lowest midterm exam grade with the same percent you get on the final. So, and I'll only do that if it helps you. So it's a way to help you, to emphasize that what you should be aiming for is to learn everything by the end of the semester. Like, that's our ultimate goal. Okay, and this is sort of a way to reward you for doing that, even if you had maybe a bump along the way. Okay. Yeah. So any questions about any of that?
What about if we didn't do well in the final exam and we did well everywhere else?
So basically what I'll do is I'll calculate your grade with this policy and without, and I'll take whatever's better. So it can never hurt you.
Okay, so another question. So on Sunday we have 2 homework instead of 1, right?
Yes, correct.
And then do we have the quiz today or?
No quiz today. The next quiz will be next Wednesday. Okay. Cool. Any other questions? Okay, well, let's jump right in. So today is another applied section. So the basic idea is we're going to take something we learned before and now use it in sort of more realistic, though they're not quite to the level of realistic problems, but they're, one step closer to being a little bit more realistic. And so what I first want to just mention is, sort of how you should approach these type of questions. So if you ever have to use math in the real world, typically the way that it's ended up working for me is when I learn math, what I try to understand, at least at the most general level, is like what types of problems does the technique I learned solve, right? So for instance, we learned the technique of finding the maximum and minimum of a function, right? So I know what that does. And you learn more and more of these techniques and you have more and more types of problems you solve. And so whenever you run into a situation, you have to ask yourself, like, sort of like, what of the techniques I have available, would be applicable to this problem? And a lot of times that's part of the hard problem in real life is determining like what type of mathematical technique would even be relevant, which is why this the way we teach it somehow doesn't emphasize that, because you know exactly which technique in each section, so it's a little bit awkward. But in this section, what we're going to be doing is we're going to be given questions who, if you think about it, for a little bit, you'll realize that we can reduce them all to the mathematical problem of finding absolute max and mins. So that should be somewhat fresh because you just all did it on the last exam. But let me remind you briefly, the type of problem that can be solved with that technique is if you're given a function, usually on an interval, though sometimes you can do without the interval, as we'll see in a minute. What we do is we find the critical values, and then we check them. Check does not have an E. And we have to remember to also include the endpoints, right? It's possible for an absolute max or min to happen at an endpoint. Okay, and then we just choose the largest or smallest output. So maybe we should say check the outputs at critical values, because it's really the outputs we care about. Right, so we're basically just going to have some word problems where we try to use this technique to solve it. Okay, so it's easiest if we just jump into an example. So take a second and read this one. Okay, so this one asks us to find the minimum vertical distance between two parabolas. So just kind of like when we did related rates, let's first always spend some time making sure we understand kind of what's going on. So often that involves drawing a picture, right? So let's sketch these two parabolas. So the first one is x squared plus 1 is an upward facing one, shifted up by 1. Maybe it looks something like this. The second one, you can notice that we could factor this one as x times x minus 1. And so it's downward facing because the x squared has a negative, and so we would expect it to go through 0 at 0 and 1. Those are the x-intercepts, which is why I factored it. And so it probably does something like this. This is 1. Okay. And so what the question is asking is, if we choose an x value anywhere, then the vertical distance between them is sort of this distance, right? And as I move x like to the right, this vertical distance is going to change, right? If I choose another x value in here, it's going to be a smaller distance, right? And so the question is, as I move x to the left and right, which x value will make that distance the shortest, the minimum distance, okay? And so, yeah, we would expect it to be like somewhere in here, somewhere between 0 and 1, we would expect from our picture, at least. It's not clear exactly where, but that's what we're going to find. Okay, so then, usually the easiest thing to identify in these problems, and the first thing you should always identify is, what is it you want to optimize? So here it's vertical distance. And then what you want to do is you want to write down what I like to call the optimization equation. It's the thing you're trying to optimize. So here I'm going to call d for distance, and we're going to try to write down an equation for this. And, because at different x values, you get different vertical distances, our distances can depend on what x is. So we're going to have an x in our equation. And if you think about how you would calculate the vertical distance here, it will always be like the top minus the bottom, right? That'll always tell you the distance is the top y value minus the bottom y value. So that would be the top y value is given by the top parabola, which was x squared plus 1, minus the bottom one, which was x minus x squared. So this is an equation that tells us for each x value, maybe to make that clear, I could even write the distance for that given x value is the difference between them. And this is what we try to minimize. And so, yeah, that's basically what you do is you apply the max-min technique to this. Okay. But there's going to be a small problem with that. Not really a problem, but it's different than what we've done in the past a little bit. So first, let's simplify. So we have x squared minus negative x squared, that's 2x squared. Then we have a minus x, and then we have a plus 1. Okay. So remember, if we're trying to find the absolute max and min, what we want to find are the critical values. So we take the derivative, and we set it equal to 0, or where it's undefined, but there's no places it's undefined. So this will give us 1x value of a quarter. And normally at this point you would ask yourself, or you would check the outputs at the critical values and the endpoints, right? But there's no endpoints here, right? And so, I mean, in this case, it's fairly clear that whenever there's a critical point in here, there's only going to be one minimum. So this will end up being a minimum, but sometimes it's not quite so clear. So if we really wanted to convince ourselves that at x equal a quarter, this will be the smallest, what we could do is we could look at the sign of the derivative. So we're basically doing like the first derivative test here. And I want to put a quarter here. So we're kind of doing exactly what we did when we graphed. And if you look at what the first derivative is, it's 4x minus 1. Right? That's an upward sloped line. And, it crosses 0 at a quarter. So we would expect it to be negative to the left and positive to the right. So indeed, right, it decreases all the way up until a quarter, and then it increases forever after. So that means this is indeed a minimum. It's both a local min, and because it decreases forever before and increases after forever, this is indeed a absolute max. So we should okay. Another thing you could have done is you could have looked at the second derivative, seen that that's just 4. So this would mean that it's concave up everywhere. So it means like, yeah, this thing had to just be sitting at the bottom of a concave up graph. So either of these things would tell us that this had to be the, absolute min, not max. That this had to be the absolute min. Okay. So yeah, the smallest vertical distance will happen when x is a quarter, but let's make sure we go back and answer the original question. See, the original question was, what is that actual minimum distance? Okay, so that means we actually have to figure out the distance when x is a quarter. So the minimum distance is d of a quarter. And you can go plug that in. Minus a quarter plus 1, which if you work it out, I'll save you the work, is 7/8. Okay. And if you want to, you could add this little bit that it occurs at a quarter. But really the important part is the 7/8. Okay. So just to reiterate, the important things that we did here is we figured out what we wanted to optimize. We tried to write down an equation for it in terms of the things that can change. So here it could be the x value that could be changed. And then we tried to apply our max-min technique that we learned before by finding critical values. And sometimes you can do the usual way by checking endpoints, but it turns out that this sort of reasoning with the first or second derivative is a lot more useful and quicker. especially if there's no endpoints and you can't do the other way. Okay, so questions about that one?
So how did we know there is no endpoint?
So it's just basically by the way the question was phrased. It just asks, if you have these two parabolas, what's the minimum vertical distance? I mean, I could have asked, what's the minimum vertical distance over this interval, but I didn't. So, you kind of just have to understand that it could be for any x. Is that? So yeah, thinking about the intervals can be a little bit difficult in some of these examples, but a lot of times you can get away without thinking about them. Okay, so here's another example. So take a minute and read this and start thinking about what is it we want to optimize. Okay. So what do we have here? So we have 800 feet of fencing to work with. And what we want to do with the fence is we want to create a rectangular shaped kind of, field or something. But it's only going to have fence on 3 sides. And the 4th side will be the lake. So what we should have in mind is like, there's lake over here. So like this is the lake. And then on the other side, we have the fence. Then we're going to try to make a rectangular enclosure here. So like these 3 sides are fencing. The black is fencing, and the blue is like water. Okay. And what are we trying to do here? We're trying to find the largest area. So that means we're trying to maximize something. Okay. So I think that's a good place to start is, you first identify what is it you want to optimize. So here we want to maximize area, the area of this rectangle. And so in order to figure out how to do that, we want to write down an equation for the area. Okay. And so we have to think about, like, what does the area depend on? Well, the area of the rectangle is going to depend on the lengths of its sides. And so, what's going on here is, the farmer is kind of considering, what shape should his field be? Should he build it long and wide, or should he build it tall and skinny? So there could be many different shapes depending on how you make the length of the rectangle look. And so the things that can vary here are kind of the length of this side. That could be bigger or smaller. And the length of this side can also be bigger or smaller. All right, and you just give those whatever names you want. I'm just going to call them X and Y. Or maybe we should call them, go the other way, so that it's more like X and Y. That doesn't really matter. And so yeah, over here now, this would be a different Y and this would be a different X. Different value of X and Y at least. Okay, and now just to be clear, if this side to the right is y, this one to the left is also y. And so, the area of this rectangle will just be length times width, or just x times y. Okay, so this is our optimization equation. It's the thing we would like to maximize. Y is a... And if we were going to follow what we did in the previous problem, we would just try to optimize this by, finding the critical values and so on. But we'll run into an issue here because there's two variables, right? And so what derivatives do we take? Do we take x derivative, y derivative, or something else? And it turns out, well, you can do either of those, but we don't know anything about the derivative of y, or x. So we have to have something else to work with. Okay, so there's something else in this problem we haven't used yet. And it's this fact that we have only 800 feet of fence to work with. Okay, so this is not something that is telling us about the thing we care about. We only care about the area, but it is telling us that we have a constraint. So it means something that we have to be true. So our constraint is that the total length of fence, let's write it as an equation maybe. So it has to be less than 800, but if we want to make this thing the biggest, we're obviously going to use all of the fencing. So we're going to have that we're going to use exactly all of the fence, and so our total length of fencing has to be 800 feet. But in terms of the variables we were talking about, we're going to have one length of fence here, one length of fence here, and then one length of fence here, right? So the total length of fence would be x plus y plus x, right? All those lengths added together have to be 800. Or if we simplify a little, or did I think I switched them. I switched x and y, so this should be y plus x plus y. And so then we would get 2y plus x is 800. Okay, so that's something we have to be true. And this is actually useful, though, because this lets us, so just like when we were doing related rates problems, a lot of times we ended up with an equation that had like 2 or more variables. And often what we could do is we could use another piece of information in the problem to replace to replace one of the variables in terms of the others. So here we're gonna get rid of either x or y. And here you could do either. Here it looks to me that it's a little easier to solve for x, so I'm just going to solve for x because it's easier. Not much easier, but a little. And so this is going to let me replace x with a formula in terms of y. So I'm going to take this x, and I throw it back up into my constraint equation so that I only have one variable left. So if I do that, now my area in terms of x only, let's go back to black, will be what? It'll be x, which is now 800 minus 2y times y. Okay, and so this is usually the first goal of these problems, is to get an optimization equation in terms of exactly one variable, because that's the type of problem we know how to solve. Is if I have a one variable function, we can maximize or minimize it, And so then we use our usual procedure. And so yeah, we want to optimize. Maybe we'll remind ourselves we're trying to maximize this. And you should think about is there an interval here or not? So you could ask yourselves, like, what's the biggest y could ever be? Well, the biggest y could ever be would be if you built your field sort of like where there's basically just two long lengths of fencing and then basically nothing in the middle, right? So basically, if x is 0, then y has to be half the length of the fence on each side. So the biggest it could ever be is half of 800, which is 400. The smallest it could ever be is, if you built your fence the other way, if you made it like super long, but not high at all. So if y was 0, then it would be all x. And so the smallest y could ever be is basically 0. Nothing negative would ever make sense because it's a distance. So this is something you could write an interval for if you wanted to. So it turns out you actually don't need to think about the interval here if you didn't want to. Okay. So now we're going to go back and use our usual techniques. So we have 800, just simplifying first. Now let's find the critical values. So the derivative is 800 minus 4y, and we're going to set that equal to 0. So if we rearrange things, we get 4y is 800, y is 200. Okay, so this is a candidate for the maximum, but we should always check that it is the maximum, right? So there are options here. So to justify that this is actually a maximum, which if you think about it for a while, there's really no way this could be a minimum or anything else. It really has to be a maximum. But in other cases, it won't be quite so clear. So it's always worth just keeping, reminding yourself of how it works. So there's basically two options here. So option one, and you only have to do one. You only have to do one of these. Is just do the usual way, and that would be to find the outputs at the critical values and the endpoints. So the endpoints were 0, then we had 200 in the middle was our critical value, and then we had 400 was the other endpoint. And if you go back up and look at A, and you see that if you plug in if you plug in 0 or 400, you both get 0. And if you plug in 200, you get some number. You get times 200, which is some positive number, right? So it's clear that this one will be the max. So that's one way, is you could do it the usual way.
So why we didn't like the numbers in the derivative function?
So why did I not plug them into the derivative?
Yes.
So if you think about it, what are we looking for? We're looking for the maximum output of the original function. Okay, so that's why I'm plugging them into the original. Okay. The second way I'm going to show you is a way you can think about it using the derivative. So these are different. So the second way is you could use the first or second derivative test. Essentially. So this would be kind of like you draw your number line, if you're using the first derivative test at least. you would put your value on here. And it's good to remember where your endpoints are, if there are any. So there's 0 and 400 here. And if you think about the derivative, so the derivative was up here. And if you think about this, this would be a downward sloping line. And it's going to cross 0 at 200 because that's what we decided it did. So it's going to go positive to the left and minus to the right. So this was indeed, it goes up and then it goes down, right? So it was indeed a max. So what we were doing here is the sine of A prime. So that would be where you were plugging into the derivative. The original one, you plug into the original function. And, kind of a third way is, instead of using the first derivative test, you could also use the second derivative test. And the way you do that is you just take the second derivative, which if you look back is just minus 4. It doesn't, so it was 800 minus 4y. The derivative of that is just minus 4. You plug in your critical value. What am I trying to say? So if you plug in your critical value, that was 200, you get the same number. And so what you'll realize here is, so maybe something I should make clear is number 2, you only want to do only if there's exactly one critical value in your interval. Otherwise, it won't tell you which is the biggest, unless one's a max and one's a min, maybe. Interval. Okay. So if there's only one in your interval, and you take the second derivative there and it's negative, well, that means you have your interval, you have your 200. And you'll realize that that's concave down everywhere. So this had to be a max. So that's another way to do it. So the moral of the story is, if there's multiple critical points, you have to use the usual way. But if there's only one, then you can use these other reasonings to maybe make your life easier. And so sometimes doing the second derivative test is very quick, right? If this second derivative test is easy. Okay, so any questions about that one? Did we actually answer the question? What is the largest area? So we got to find the area. So what we decided was that 200 is the proper value for y to maximize it. And so the area will be here. So our final answer would be maximum area is A of 200, which was 800 times it was 800 minus 2y times y. Now we plug in 200 for y. So this number again, which if you work it out will be 8 with 4 zeros. Okay, and each length was in feet, so overall it'll be in square feet, feet squared, because it's an area, which is length squared. Okay, so now any questions? Okay. So we're going to look at another one. So take a minute and read this one and decide, what are we trying to optimize? Alrighty. So in this problem, we might imagine ourselves, we're at a company that makes something, and your boss asks you to design, packaging for something, and they give you some requirements, right? So you're going to make a box. The total volume of the box has to be 10 cubic meters, but it's not going to have a top. The box is going to be made out of 2 different materials. So for the bottom of the box is going to be made out of something that costs $10 for every square meter of area, and the sides will cost $6 for every square meter. And there's one additional constraint, that the length of the box has to be always exactly twice the width. And of course, you're a company, you want to minimize your cost. So we're going to try to minimize the cost to make one of these boxes. Okay, so let's think about what this box looks like. Let's draw a box. One of these sides should be longer. So you get a box that looks something like this, right? And it doesn't have a top, so we can sort of see inside of it. And then, yeah, what do we do with this box? So, I think the easiest thing to recognize is, first, what is the thing we're trying to maximize or minimize? So here we're trying to minimize the cost. So our optimization equation should be an equation for the cost. So let's start thinking about our optimization equation. So I'm going to call C for cost. And then you think about, if you start making this box out of materials, you're going to have to cut up some pieces and glue them together or fold them, or, who knows how exactly the box is constructed. But, there's going to be a certain amount of material for the sides and a certain amount of material for the bottom. So you're going to have some area of material for the sides and some area of material required for the bottom. And for each unit of area, which are meters squared here, for the sides, it said the sides cost $6 for each unit of area. So it's going to be 6 times the amount of area for the sides. And then you have to add to that the amount it costs for the bottom, which will be 10 times the amount of area you need from the bottom. Okay, so this is sort of like the cost function in terms of words. Now we need to somehow figure out what are these areas. And well, it's similar to before, right? You could have different shaped boxes. You could have a box that's sort of the opposite shape. Maybe one that's longer and skinnier, though this one doesn't look like it has, well, maybe it does. Yeah, that's ugly. But the point here is you might have another shaped box. Let's just get this part right. God, that's horrible. Anyways, you could have a different shaped box. And so the point is the things that can change here are the height. So you might give that a name because that can change. You could make the height different. You could have maybe this side length, which, I don't know, maybe I'll call that the width, and maybe call this the length. Doesn't really matter, as long as you give them different names. But those are the things that can change, are those side lengths, right? And those determine the cube. And so in terms of now our cost, so let's first look at the sides. So there's kind of two different shaped sides here. So on this, there's this side, which will be the same dimensions as this opposite side, right? I've put yellow dots on the sides. And so if you think about it, like, because it's height, h is also here. And so those will contribute, each one will have area h times L, and there's two of them, so it'll be 2HL from the yellow ones. And then you have these other two sides, which maybe have different dimensions because it's width instead of length. And those each have area WH, and there's two of them. So you get 2WH. And that's all the area for the sides. And then you look at the bottom. So the bottom has, length times width. That's its area, so that's LW, and there's only one of them because there's no top. If there was a top, there'd be two of these. Okay, so this is essentially our optimization equation. But we run into this issue where there's too many variables, right? So our next goal is to figure out a way to get this down to one variable. So we can, take the derivative, set it equal to 0, and do our usual technique. And so whenever we're trying to reduce things to one less variable, we should go and look at, like, what are the constraints? What was the other information that had to be true about this box? So there were two things. The volume had to be 10 cubic meters. Let's write that down. So let's talk about constraints. So the volume has to be 10 meters cubed, which, if we think about it in terms of our variables, it's just the volume of the box is length times width times height. And let's see, was there anything else? Yes, there was the second part where it says the length must be exactly twice the width. Okay, so in terms of equations, that would say that L has to be exactly 2 times W. Length has to be twice the width. Okay. And so, yeah, you have to decide on, like, what variable do you want to use in your optimization equation. And usually there's multiple choices. In my mind, the easiest one here is to get everything in terms of W's. Because L is already in terms of W here, right? L is 2W. So that would mean, next I would want to also get H in terms of W. because I need to get rid of H's and L's if I'm going to get everything in terms of W's, right? So the second one tells me how to get rid of L's. Now I need to figure out how to get rid of H's. And the way you might do that is you would take this and throw this into here. So if you combine these, you get 10. And instead of L, I'm going to write 2W. And now this is an equation that only involves W and H, so I can solve it for H. So you get something like that, which if you simplify is 5 over W squared. Wait, where did the 4 come from? This should be a 2. And now it's 5 over W squared. Okay, and so this tells me how to get rid of H's and how to get rid of L's. And so now I'm going to take the L's, plug them in, and I'm going to take the H's and plug them in, wherever I see them in my optimization equation. Okay, so let's write that out. So let's see. Our optimization equation with one variable now will be 6, okay, 2, and then H gets replaced with 5 over W squared. L gets replaced with 2W plus 2W. H gets replaced with 5 over W squared. Big parenthesis, maybe just for clarity. Whoops. I'm going to use different types of brackets so we can see them. L gets replaced with 2W. Okay. So if we simplify this a little bit, okay, so we'll have 12 times 5, that's 60, times 2 is 120. We're going to have a 120, and then W over W squared is over W. Okay, second term will be 6, right? Because remember, the 6 goes on both, right? So it'll be 60 over W. And then the third term is just a 20W squared. You can combine these fractions, and you end up with something like this. And this was our goal, is to get the optimization equation into something that just has one variable. It's an equation that just involves one variable. And this is it. And now we, apply max-min technique. Okay, so we take the derivative. So the derivative at different values of W, I guess. So the derivative would be minus 180 over W squared plus 40W. Want to find the critical value, so we set it equal to 0. And there's many ways of solving this. Let's maybe just throw the 180 to the other side. Then maybe we'll bring the W squared up over here. Multiply through by W squared, so we get 40 W cubed equals 180. W cubed equals 180 over 40, which is 9/2. Then we can take both sides to the 1/3 power to get W alone. And this will tell us that W is this funny number, cube root of 9/2. Okay. And so now we should decide, like, is this actually a minimum, right? Because we're trying to minimize the cost. You want to be careful and not pick something that's like a maximum somehow. because all we knew is that the derivative was 0 here. We don't know if it's a max or min for sure, though you could probably reason out that it has to be a minimum here. But it's good to just check. And so you could go through and worry about all the intervals and stuff, but an easier way is to just jump directly to the first derivative test. I think that's easier than the second derivative test here. So you would put the 9/2, our critical value, on your number line. And you have to be a little careful, because if you think about it, our original function had division by 0 at w equals 0. So 0 is not a valid point because it's a vertical asymptote. But now what we're doing is we're checking the sign of the first derivative. So that was here. And an easier way to see what the signs would be, you can just plug in points if you want. So like a point to the left here, you might choose like 1 in this region, and maybe just choose like 100 over here, or 1,000, or whatever you want, because there's not really any upper bound. And so if you plug in like 1, you'll see that it's a negative because the 180 dominates. So here you end up with a negative. If you plug in a really big number, this will be really huge, and so this part will be, the first term will be small, and the second term will be big and positive. So the second one will end up being positive. But if you're in doubt, you can just plug in like a number like 10 or 20 or 100 or something. And so what you see here is, yeah, function's going down, 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 then it hits this value, and then it goes up forever afterwards. So it had to be a absolute min there. Okay. So what we concluded is that the absolute min happens when w is cube root of 9/2. Okay, that's good. So that basically answers the question, but let's make sure we answer what was actually asked. So what was actually asked was, what dimensions minimize the cost? So that means it wants all the dimensions. So we have w. So we also need arg h, and we need L. Okay, well, L, we remember, has to be twice the width. So that'll be just twice this. But H, well, at one point we had H in terms of W, right? Because that's how we replaced it. So if you look at this equation, it says H is 5 over W squared, and we know W. So H will be 5 over 9/2 to the 1/3 squared. Now let me just move this down a little. Okay, so those would be the dimensions, and include units if they're applicable. So this was talking about square meters, so these lengths would just be in meters. Okay, and that would be our answer. Okay, so questions about that one? Okay, so if there's no questions, that's going to be it for today. If you want to see more examples, you can go look at our weekly plan, and there's like 4 videos that have a whole bunch of examples. You can watch those. We'll also be probably doing 1 or 2 more examples on Friday. as well as a little bit of other stuff. So I'll stick around for a little while if you guys have questions, but other than that, have a good day, and I'll see you on Friday.